of several variables. I'll explain what that means in a moment, but I'd like to start with this. This is basically a technique from statistics. And this is where we normally teach it. But why is the least squares technique in this chapter? Is because when we talk about least, we talk about minimum. And when we talk about minimum, we talk about calculus. That's why this technique appears in calculus as well as statistics. What does it mean? Okay. So let's suppose I measure everyone in this class. Let's say I measure your height and blood pressure. So the first person has x1, y1. The second person has x2, y2. The next person has x3, y3, and so on and so forth. And let's say I plot these points. x1, y1 is this point. x2, y2 is this point, and so on and so forth. We are interested in prediction. So trend. We want to see the trend or predict outside of this or even inside of it, of this domain. And we realize that this cloud of points kind of appears to be linear. It appears to follow a linear function. Of course not. The linear function cannot go through all these points. But we call this line the line that has the least squares error. What the least squares mean? Okay, this distance from the point to the line, this distance from the point to the line, this distance from the point to the line. All these distances are minimum. So this is the line of best fit. This is the line that best fits x, y points. If it's linear, it could have other trends. We're only going to talk about the linear situation. Just the linear situation. So let me show you an example how this is used. I'm going to share my screen. I'm going to go directly to an example. No work is required by hand. Everything is just done with a graphing calculator. Nothing else. Okay, so let's take a look at any of these examples. Let's read this 11. If I can find and go back. Yes, here it is. Okay. Life expectancy of women. Consider the data in the following table showing the average life expectancy of women in various years. And here's the table. I will copy the table on paper. So this is 11 on page 582. And I have X, as I mentioned, X and Y. So this is since 2004. And 0 and 2, 5, 7, 10, 79.96, 80.21, 80.81, 80.95, and 81.11. I go to the graphing calculator. All I need to do is go to stats, of course. And we want to add, let me start from scratch, and I want to record this. Where is my recording? Where is my recording? Yes, record on this computer. Perfect. So we go to stats, edit, enter, clear the lists L1 and L2. Go up, highlight L1, clear, enter. Go up, highlight L2, clear, enter. And I have to enter the data exactly how I see it in the table. So 0, 2, 5, 7, and 10. Move to the right to L2, 79.9, 96, 80.21, 80.81, 80.95, and finally 81.11. Good. Get out of there with second and quit. Go back to stats, but this time we want to perform calculations. So go to the right and come down to number 4, linear regression. The line of best fit is called the linear regression line. I'm going to write that for you here. Line of best fit is called linear regression line. So we go to number 4, or just click on 4 and then enter. It's asking you which is the list L for x values, or it's list L1. It's asking me now what is the list for variable y. Yes. It's asking me if I want to store the linear regression line somewhere. Yes, of course I do. I will click on variables. I will go to y variables. I will choose function y1. And then I will just highlight calculate. And I get the linear regression line is y equals a number a, this is the number a, times x plus a number b, which is this. Of course, this is the slope as we know it, mx plus b. It's called a in the calculator, but that's what the slope is. And b is the y-intercept. So I'm going to copy y equals point, let's say we use 3 decimal digits. 121x plus 80.025. We do not need the correlation coefficient and the correlation of and the coefficient of determination. We are not discussing these in this class. We are only interested in the linear regression. Now, when you click on y equals, you will see the linear regression is already in there because we saved it. We told the calculator to save it in y1. Now, the question also is asking us, use the regression line to predict the life expectancy of women in 2025. So this is 2004, so 2004 plus 10 is 2014. We have to always be very careful when we predict the life expectancy too far out of the data set. So the data set is between 2004 and 2014. You may say, well, 11 years is not too far out. Okay, but the pandemic happened, and that probably changed the linear regression line by a lot. So coming back, I can simply go back to second and table. We are asked in 2025, which means 21 years after 2004. So I will plug in 21, and the calculator will give us 82. So y equals 82.58 when x is 21. 2005 minus 4. I'm going to stop the recording. So coming back here, this is the linear regression line, and when x equals 21, the life expectancy for women appears to be 82.58, assuming the regression line is still valid in the year 2025. Now, the other quick thing that I wanted to show is if we plot this, because that's we are told find the linear regression line, but normally we are not told that. We have to discover whether this is a linear regression situation. It could be quadratic. It could be exponential. I don't know. How do I know this is linear? Just because they told us. But I just wanted to show you, and we'll move on from here, unless you have questions. So if you want to plot, so you can plot the points, but you have to, so I'm going to put this on, of course, turn it on. This is the scatter plot. List L1, list L2, but I have to change the viewing window. X between, let's say I have 0 and 10. I'm going to make it 0 and 20 with a scale of 5. But as you see, Y minimum or Y values are somewhere between 75 and 85. So 75, 85 with a scale of 2. So that I can see that this, the data set, otherwise I won't be able to. And when I click graph, look what happens. It shows, the calculator shows the points and also the linear regression line. The line of best fit, the line with the smallest possible error. And that's it. That's all we need to do in section 6.4. Only calculator work. Any questions about this? Do we need to look at another example, or is it clear?
How do you save it again?
Yes, so you mean the linear regression?
Yeah.
So also it's recorded. I will post it, but how we do this, so we go to stats and calculations, go to 4, and you may not have this feature. Not all calculators have this feature. Let's say I don't have this feature. If I don't, when I determine the linear regression line, I just go in and put it in by hand. And exactly what I had here, 0.121x, but I have to delete the whole thing because it has so many decimal digits. 0.121x if you don't have this feature, plus 80.025. So if you don't have that feature that allows you to save directly in Y1, then you have to enter it by hand. And yes, the answer will be slightly different. Not by much, but slightly different because we truncated the slope and the y-intercept. We don't have the number of decimal digits that the calculator saved. Does that answer your question?
Yes, thank you.
Thank you. Sure. Is this clear? The line of best fit is the line that has the least error. Of course, no line can go through all points. I doubt if it goes through one. So, but this line has this least amount of error. This one will not. This one will not. This one is the one that has the smallest error in the form of distances squared. No calculus is required. The calculator does all the work for us. Any questions? Do we need to illustrate with another example, or can we move on?
I just have a quick question.
Sure.
On the calculator, how do you know which scale to use for X and Y?
Which scale?
Yes, you did X, a scale of
0
5,
to
Y,
10, 0 to
Okay.
10, 75 to 85.
No, the scale.
When you say the scale in the viewing window, this one?
Yes, yes.
Well, I don't see if I put scale of 1, the calculator will show me these ticks, like millions of ticks between this and this. I don't want to see millions of ticks. So between 0 and 20, with a scale of 5, it will show me 4 ticks. So it's not too crowded. See, it shows me 4 ticks, and I know that this is 5 and 5 and 5 and 5 and 5, between 0 and 20. It will be more difficult to read if I have many of them. So it depends. So the scale depends on what I have. So this is 10. So I want the scale of 2. If I put a scale of 10, it's not going to be a big deal, but it will be easier for me to read 2, 2, 2, 2, 2.
Okay.
The scale is not super important, but it's important for me to be able to read the points. So it's all based on what I have. It's between 0 and 20, scale of 4, 5, 5, 5, 5, 5. Between 75 and 85, 10, distance of 10, scale of 2. So it depends on these numbers, between 0 and 20, and between 75 and 85. That's how I choose the scale. Good. Moving on then. Now, section 6.1, finally, we talk about functions. Let me see how I'm with the time here. Let me